Hello, everyone. Welcome to all of you in my lecture today. In previous lecture that I have started from mass transfer in chemical engineering. So, in previous lecture, already I have discussed that was the lecture number one. So, already I have discussed about the concept regarding mass transfer and the basics of the mass transfer and the various concentration terms and types of flux were there, right? So, today, from today onwards, I am discussing about these fluxes, right? So let's try to understand about the flux. So already in previous lecture I have discussed about the diffusive flux and molar flux. So today we'll see about the relationship between diffusive flux, molar flux, and the total flux, right? So I am starting with the concept of relation between that is Ni and Gi, right? So here you can say Ni is our convective flux and Gi is diffusive flux. I hope up to this the concept is very clear to all of you that that terminology that Ni and Gi. So now we'll have to find out the relation between these two particular terms, right? So in the previous lecture that I have discussed about the formula that how can we define the Gi. So Gi is defined on the basis of molar average velocity Vi minus V bar. That is Vi minus V bar, and that is average velocity. And already I have discussed you how we can calculate the average velocity that V bar. You can write summation of Ci Vi divided by summation of Ci. If this is a system in which lots of number of molecules were there, so everyone is moving with the particular velocity V1, V2, V3, that is V1, V2, V3, V4, V5, and having concentration C1, having C2, having C3, having C4. So we can calculate that Ci into Vi upon summation of Ci. So that was the term. So now we have written that term Ji that is equals to Ci, and you can write Vi minus V bar, right? So now you can write that Ji that is equals to Ci Vi minus Ci V bar. So you can write Gi is equals to Ci Vi minus that Ci, and summation of Vi is equals to, sorry, Vi bar is equals to summation of Vi upon Ci Vi upon summation of Ci, right? I think it's up to this everything is clear now. So now I can write that Gi that is equals to Ci Vi, we can write it is as a Ni minus Ci divided by summation of Ci into summation of Ci Vi, right? So now for the what we can write that is Gi is equals to Ni minus this particular term you can call it as that is the mole fraction, right? So you can call it Yi multiplied with summation of Ci Vi, right? So this is our diffusive flux, this is our convective flux, right? So finally, what we can write that Gi that is equals to Ni minus Y into N total, right? That is N total. So again, I am writing this formula Ji. So if you want to write Ni is equals to Ji plus Yi into Nt, where Nt is equals to summation of Ni. And you can also write it as Nt is equals to N1 plus N2 plus N3 plus dot dot. What is this thing? If there is a system of molecules is there, so having first molecule that is one, second molecule that is third molecules, four molecules, and these are the convective flux related to that molecules is that is N1. that convective flux related to the molecule is N2, that convective flux related to the molecule 3 is N3, and that convective flux related to the molecule is N4. So if you are able to sum of all these convective flux, that is N1 plus N2 plus N3, then it will give total convective flux, and this is the appearing in this formula, that Ni, that is convective flux of individual molecules, that is equals to Ji, that is diffusive flux of that individual molecule, plus Yi, that is the mole fraction of that molecules, mole fraction, and that is total flux. That is total flux. So don't get confused that NT is equals to NJI plus Ni. No, it's convective flux, sum of convective flux of the all molecules, right? So now I'm taking for the binary system, right? If there are only two components, if there is a system in which component A is there and component B is there, right? So can I write that? So we can write NA is equals to JA plus YA multiplied with NA plus NB, right? And I can write that is NB is equals to JB plus YB multiplied with NA plus NB, right? And now if we add, that is if I am assuming this equation first and this is the equation second, so if we add equation first plus second, then what we get? Sorry, that Na plus Nb, that is equals to Ja plus JB plus, if you took common Na plus NB, then here you will be getting Ya plus YB, right? So now what you will get, that Na plus NB, that is equals to Ja plus JB, right? Plus Na plus NB. Why? Because you can say that Ya plus YB, sum of mole fraction is equals to 1, right? So from here you will be getting Ja plus JB is equals to 0. Or you can write Ja is equals to minus JB. So by any means, if in the problem it is given that you'll have to calculate the something for B, then if J is given, then you can calculate the JB, right? So this is the thing that you need to understand. So I have taken this particular problem for the binary system, but if there are a multi-component system is there, having component J1, sorry, J1, J2, J3, J4, J5. So you can write summation of Ji is equals to 0. What does it mean? So you can write J1 plus J2 plus J3 plus dot dot Ji is equals to 0. I mean, the sum of the diffusive flux of all the component will be equals to 0 in a particular system, right? I think up to this everything is clear now. So now I will be moving forward for this particular topic, and now going towards the very important concept of the diffusion, and that is the Fick's law of diffusion, right? Fick's law of diffusion. So since here in this problem, in this particular topics, we are studying about the diffusion. So it's a very important and fundamental law for the diffusion that we need to understand here. So the Fick's law of diffusion said that the diffusive flux relative to any average velocity of the fluid mixture in the absence of any convective transport, the diffusive flux and total flux will be same, right? So if, see, one thing is that if there is no any convective flow, so what does it mean? In the Fick's law of diffusion, what does it say? So first, if you want to calculate Na is equals to Na plus Ya into Nt, right? So if this total Nt is equals to 0, then what will happen? Convective flux will be equals to diffusive flux, right? And next is that since flux is a rate of mass transfer per unit area, per unit time, normal to the direction of the transport, right? So here what will happen? Here, since Fick's law is only applicable for the diffusive flux, right? So try to understand, it is only applicable for, diffusive flux, and the diffusive flux I am denoting it as a Ji. So Fick's law says that Ji is directly proportional to that concentration gradient, right? So if this is our point 1 and this is point 2, and if our component A is diffusing, so if here that is Ca and if it is Cb, and here if it is distance is I am assuming that dz, so Ji is directly proportional to dCA upon dz, right? dCA upon dz, that is negative sign. Why? Because here concentration will be more, here concentration will be less. So dCA that will be equals to Cb minus Ca. Or I mean, here I am writing, sorry. So better don't get confused. I am writing here that is C1 and C2. So that will be the concentration of component A at point 1 and Y at point 2. So it will be very easy for you to get that I am writing, that is C1 and C2. So it will be equals to C2. Here you can write C2 and here it is C1. So C1 is greater than C2. So dCA will be less than 0. So that's why we are using that negative sign here. And Ji is directly proportional to the area, that cross-sectional area, right? So if this is cross-sectional area, so it is flowing like that, I am assuming. So directly proportional to cross-sectional area, right? So yeah, so we can write now Ji that is equals to, if we remove the proportionality constant, that you'll have to substitute a constant term, that is d. I'll let you know what is d. D into area, and this is equal to dCA by dz, right? And if you want to write that rate, so rate is equals to Ji upon area. So here we are writing flux, so better to write in terms of, it's very important to understand this is diffusive flux, that is per unit area, right? So here I have written that is Ji is equals to minus d dCA upon dz. So where d is diffusion coefficient. So what does it mean? How can you define diffusion coefficient, right? It's a that you should know. So if we want to write d, that is equals to Ji upon dCA upon dz. So can we define diffusion flux, that is the, if for any particular cross sectional, if our diffusive flux is equals to 1 per unit concentration gradient, right? So you can define that the ratio of unit diffusive flux per unit of concentration gradient. This is the diffusion coefficient of any particular substance. So if you want to measure the diffusion coefficient of any particular substance, just like oxygen, carbon dioxide, or naphthalene, then what will you do? So for a particular diffusive flux, if the concentration gradient is unity, right? So in that condition, that ratio will give you the diffusion coefficient, right? So from there, you can measure the diffusion coefficient of the particular substance, right? Now coming to the next point. So when we talk about the binary mixture, right? So if component A and component B is there. So what do you mean by it? So by Fick's law, by what I can write, that Gi is equals to Di dCi upon dz, and there will be a negative sign. So in a binary mixture, what you can write, that Ja that is equals to minus Da dCa by dz, and Jb. So in the mixture, what you have to write here, that is DAB. And here in the mixture that you'll have to write dBA and dCB upon dz, right? Now, next thing, earlier what I have told you that if you want to write that Na, that is the convective flux of component A, Na is equals to, you can write that is, now we know the value of Ja and Jb, so we can write that J and Jb term here. So here it will be Ja plus Ya into Nt. Are you getting? So I can write Na is equals to J is equals to minus dAB dCA upon dz plus Ya, and here you can write Na plus Nb, right? And for Nb you can write minus dBA dCB by dz plus Yb, and this will be equals to Na plus Nb. I think up to this everything is clear why I am writing this particular formula. Now, uh, when again, if I am assuming this equation is third and if I am assuming this equation is four, so what will you get now? So if I'll add equation third and equation four, so you will be getting Na plus Nb, that is equal to minus dAb dCA by dz plus, if we'll add this term, so it will give you Na plus Nb, Na plus Nb. Already I've done this earlier, and again that will be equals to minus minus dBA dCB by dz. So this term and this term will get cancelled out. So can I write here dAB dCA by dz, that is equals to dBA dCB by dz, sorry, plus, that is equals to 0. No, can I write? See, one thing is that from here, most of the time you'll see the problem in the net. So that's why I'm driving all these things. So I have written that DAB dCA by dz plus dBA dCB by dz, that is equals to 0. So can I write DAB upon dBA, that is equals to dCB by dz divided by dCA by dz. So from here you will get that ratio of diffusion coefficient of component A and B in a mixture, that is equals to the concentration gradient, inversely proportional to the concentration gradient here. So I mean you can see the problem on the proportionality also. So yeah, so it's very important. Now the next thing is that for a binary mixture, right? If we talk about for a binary mixture, what happens? We'll see for a binary mixture, dCA by dz, that is equals to minus dCB by dz in the liquid. Why? Because C total is equals to Ca plus Cb. So dC total by dz, that is equals to d upon dz of Ca plus Cb. Are you getting? So dC total concentration will be constant. So it will be equals to 0. So that is equals to dCA by dz, that is equals to minus dCB by dz, right? From here I am writing these things. Now next thing is that what are the findings that you can get here from here, that I have written that dCA by dz, that is equals to minus dCB by dz, इसलिए so you can write DAB is equals to minus dBA, right? So if two components system are there, that A and B, so if by any means if you are able to find the diffusion coefficient of component A, that is DAB, so With the help of this particular correlation, you'll get the value of dB also. So no need to worry about that. If the system is binary component, then it is very easy for you that you'll get the thing very in a simplified manner. Now, moving forward for this particular topic, I'm going to discuss about some steady state molecular diffusion in the gaseous condition, right? So first, I will be discussing about the equimolar counter diffusion. Equimolar counter diffusion. So every alternate year, you'll see a question is coming from either equimolar counter diffusion or diffusion of A through non-diffusion B or some basic concept. But definitely you'll see a problem on this particular topic in every year, right? In the gate. So even if in the mark also or any examination related to chemical engineering, you'll see this kind of problem that is coming in the examination. So I'll suggest you be very precise and be very focused about this topic. It will take some time, but yes, get us towards the topic and make this topic very strong. So when we talk about the equimolar counter diffusion, so what happens in equimolar counter diffusion, the number of moles of A moving in one direction will be equal to the number of moles of B moving in the opposite direction. I mean, what is happening here? Just try to understand. If this point is 1 and if this point is 2, and here if A is moving, then here from this direction this B will be moving. So there will be equal number of A moving will be moving from 1 to 2. So the number of equal number of B will be moving from 2 to 1. This is the concept behind this particular equimolar counter diffusion, right? So in this case, what happens with respect to the stationary observer, you will see there is no net molar flow in either direction. See, one thing is that what is happening. Uh, you can see such kind of examples, right, in day-to-day life. If you want to see this kind of example, see directly you cannot see this particular example on the by the naked eye, right? It's occurring on the microscopic level, so it's very tough to analyze the thing. But yes, I mean in day-to-day life you can analyze, right? Mm, Generally, this kind of thing happens in the distillation column, but you cannot see directly, right? So, with respect to C, observer is here, right? So, you are observing the thing from here. You are observing the thing from here. So, see, the diagram is not up to par, but try to understand the thing. I'm trying my way. See, you are observing this particular phenomena from here. So equal number of A is going towards 1 to 2 and equal number of B is going towards 2 to 1. So you won't see any movement happening inside the system, right? Because you are stationary, so you'll find that nothing is happening, right? So that's why I'm telling that with respect to the stationary observer, since you are here it is a stationary observer, so you cannot see any movement, right, happening inside the system. Next thing is that uh, one very important point. This particular example has been seen in the the enriching section of distillation column. So that enriching section of the distillation column. So what is happening here? So equal number of A will be moving. So can I write that Na is equals to minus of Nb? This is the phenomenon. This is mathematical thing. And equal number of A is moving towards equal number of B and C. So this is just a statement. So if you want to make this statement into the mathematical formula, so you will have to write that Na is equals to minus Nb. So can I write Na plus Nb that is equals to 0, right? Are you getting it or not? Right? So when we talk about that Na, we can write that is equals to Ja plus Ya into Na plus Nb. Are you getting? So when we talk about the equimolar counter diffusion, since N is equals to minus Nb, so this term is getting 0. So you can write that Na is equals to J. Are you getting? And from the diffusive flux from the fixed law, you can write that minus dAV dCA by dZ. So can I write Na is equals to minus dAV dCA by dZ for the equimolar counter diffusion, right? Now, since if I am assuming this system is this is happening in the gaseous system, so can I write Ca is equals to partial pressure of A upon RT? So you can write Na is equals to minus dAB upon RT and dPA upon dZ. Now, since I am assuming that component A and B both are there in this system, so partial pressure of A will be there, partial pressure of B will be there. So can I write Ya is equals to uh, partial pressure of A upon P total. So partial pressure of A that is equals to, can I write PT into Ya. Are you getting? So again we can write Na is equals to minus dAB upon RT, and you'll have to multiply with total pressure PT, and you can write dYA by dZ. So since try to understand this thing, since it is zero point 0.1, it is zero point 0.2, so mole fraction of A here is Ya 1, and here mole fraction of A is Ya2. Mole fraction of B is Yb1, mole fraction of B will be Yb2. If this distance is Z, right? So we are basically trying to find out that Na is equals to minus DAB here, that is PT divided by RT and dYA upon dZ, right? So can I write Na into dZ, and Z is equals to Z1 to Z2, that is equals to minus DAB into PT upon RT, and here dya, and ya will be varying from ya1 to ya2, right? So can I write here Na into Z2 minus Z1, that is equals to minus dAB into PT upon RT, and here it will be ya2 minus ya1. And since ya1 is greater than ya2, so you can write Na, that is equals to dAB into PT upon RT into Z2 minus Z1 into Ya1 minus Ya2. I have done nothing, only made this negative to positive. Now, so basically the formula you are getting here is Na is directly proportional to Ya1 minus Ya2 upon Z2 minus Z1. Right. So, if try to understand one thing, what will happen? Since this will be Na, this flux, if I am assuming Z1, Z2, Z3, if I want to find out that particular mole fraction of A, that particular Z3 level, so what you can do, so this is proportionality equation. So can I write Na1 is equals to Na2? So I can write directly what Ya1 minus Ya3 by Z3 minus Z1, that is equals to Ya1 minus Ya2 upon Z2 minus Z1, right? So this is the distance only, right? This is the distance, right? So only that Z3 minus Z1 is that Z3 minus Z1, this distance. Z2 minus Z1 is this distance. Only you'll have to substitute the magnitude, right? So this is what I am trying to let you understand the thing with the help of the equimolar counter diffusion. So you can see uh, uh, which kind of profile you will see here, right? So that becomes very important. So here, uh, when we talk about Na, that is equal to minus dAV dCA by dZ. So dCA by dZ, that will be constant. So dCA by dZ will be constant, right? So it should be like, I think, something that will be CA1, that will be CA2, and here that is Z1, that is Z2. This kind of profile you will see right here. dCA by dZ, that slope will be constant completely. Slope will be constant. So this kind of slope you will see, right? So this is what I'm trying to convey in this particular topic lecture, that how the profile look like. So let's try to understand that I'm deriving the concentration profile for this particular thing. So try to understand. So here we are moving towards this direction. So I'll be taking a small strip here, right? I will be taking a small strip in between. So what does this strip mean? Try to understand. I'm applying the cell balance. So here it will be Na at Z if the thickness of this strip is dZ. So here the flux coming out is Na at Z plus dZ. So what will happen? Na bar at Z minus Na bar at Z plus dZ, that is equals to 0. So can I write dNA by dZ, that is equals to 0? dNA by dZ, that is equals to 0. Means, what does it mean? What does this particular thing signify? Means the variation of that flux Na dNA bar by dZ, that variation of Na bar with respect to Z is 0. Means variation of Na bar with respect to Z is 0. What does it mean? Na bar is not the function of Z. Na bar will not be function of Z. It will be constant throughout. Na bar will be constant throughout. So what you can see, Na bar, that is equals to Na into area. So you can write Na bar is equals to Na1 into A1, that is equals to Na2 into A2, that is equals to dot dot constant, right? So this is the thing that I wanted to say. So you can write again d by dz of Az into Na, that is equals to 0. This is very important thing, and most of the time, I mean, in coming future you may see this kind of problem in your gate, right? So I'll suggest you to focus on this particular topic the way I am teaching, and will in the subsequent lecture we'll be focusing some numericals about this particular cumular counter diffusion also, right? And in the next lecture I'll be discussing about the diffusion of a through non-diffusion mode. Okay, hope I have tried my best to let you understand the topic, and go through this video and try to solve the problem. Okay, thank you. And if you find this video is very relevant to you, please try to share in your group with your colleagues, okay, so that I'll get motivated and will be coming with more potential and more energy in the coming lecture, right? Thank you.